Section 7-3, repeating decimals. In this section, we're going to look at when a decimal turns into a repeating decimal, the parts of that decimal that we'd like to identify. We're also going to look at how to take that repeating decimal and transform it back into a fraction. We know that terminating decimals can be translated between fraction and decimal form in a couple of different ways. One of them is making a power of 10 in the denominator. So if we're starting with a fraction like 7/8, we know that 8 is the same thing as 2 to the third power, which means to make a power of 10 in the denominator, I need to multiply by 5 cubed on top and bottom so that I can have 10 to the third power or 1,000 for my denominator. And then from there, we can just use our place value knowledge to rewrite this as a decimal. We could have also used long division. So if we have 7 divided by 8, we would put 7 inside of the division symbol. 8 goes on the outside as the divisor. We know 8 does not fit into 7, so then we consider 8 into 70. 8 times 8 is 64, so I'll copy the decimal up to the quotient place, and then I'll subtract 64. This is kind of our repeated subtraction idea in long division. And we keep dividing. And because this is a terminating decimal, we will eventually have a remainder of 0. Now, if we didn't have a remainder 0, we would add zeros on to the dividend until we get to a remainder 0. However, sometimes we will never get to a remainder 0, and in those cases, we're talking about a repeating decimal or an irrational number. So in a terminating decimal situation, we can either make a power of 10 in the denominator and then translate that to a decimal, or we can use long division until we get to a remainder 0. And then we know we're done converting the fraction into a decimal. With repeating decimals, for example, we might have a factor in the denominator that is not a 2 and not a 5. 11 in this case is our denominator. There is no such number that I can multiply to top and bottom so that I get a power of 10 in the denominator. It doesn't exist, which means we can't use that method. So maybe we're stubborn and we say, well, there's got to be a way to turn this into a decimal, so we use long division. We would write that as 11 going into 2. 2 is a whole number, so the decimal is right to the right of 2. We know 11 does not go into 2, so I'll put a 0 above the 2, copy my decimal, and then I'll turn my 2 into 2.0 so that I can ask how many times does 11 go into 2.0, or 20. In this case, we know 11 would fit into 20 once. We'll subtract our 11. We have 9 left over. Now, a remainder is not 0, so we would keep going by extending 2 with another decimal, bringing it down so that we can look at how many times 11 goes into 90. In fact, it'll go in 8 times because 8 times 11 is 88, which means we would have 2 left over. Now, this is, again, not a 0 remainder, so we would need to keep going. So we can add a 0, bring it down. 11 goes into 20 once. Subtract that 11, we're left with 9. Add a 0, bring it down. 11 goes into 98 times. Subtract off the 88. We're left with 2. We still don't have a 0 remainder, and so we can keep repeating this process, but maybe we're already starting to predict that we're going to end up with the same pattern over and over and over. And if you're able to recognize that, awesome. If you're not, let me help point that out to you. We started off by asking how many times 11 goes into 2. that same question came up right here. And then it happened again right here. And then it was about to happen again, but we stopped our division process. 11 didn't fit into 2, so we said 11 into 20. Again, 11 into 20. Again, 11 into 20. And if I added another 0 at the end of my dividend, I would be asking again 11 into 20. This is a key indicator that you're going to have a repeating decimal, because you did a few divisions, you did some subtraction, but you end up essentially in the same spot that you were in before. So remember, we were 20, 20, 20, 20, but also maybe you noticed that after the 20, we had 90 each single time. And that's why we're getting a 1, 8, 1, 8, 1, 8. And you could imagine that this would keep going forever and ever, and there's no reason for it to stop. So for this fraction, 2 over 11, we wouldn't just write 0.18. We would need to signal that that 1/8 pattern continues indefinitely. We can do that by putting 3 dots as in ellipses to say this pattern continues, or we can use the over bar. Drawing a bar over both digits 1 and 8 tells the reader that it's the 1/8 that will repeat in the pattern. We call that the repetend. So in this case, we have a repetend that looks like 1/8. And then the period is how many digits are in the repetend. In this case, our period is 2 because we have the digit 1 and the digit 8. Therefore, there are 2 digits in the repetend. We have a period of 2. To become more familiar with the repetend and the period, let's do a couple of examples where we look at fractions written as decimals, and we're just going to use a calculator to compute these. So the fraction 1 divided by 7, we can type in 1 divided by 7, and we can see that we have a decimal here. In fact, if I drag this calculator out, technology is pretty great these days, I'll see more digits. Now, this is something that can be tricky. When you type a fraction like this into your calculator, it might look like it terminates because eventually the numbers stop. But if you pay very close attention, it does appear that we're repeating 1, 4, 2, 8, 5, 7. 1, 4, 2, 8, 5, 7. 1, 4, 2, 9. What happened here is the calculator is only capable of showing so many digits. So it does a rounding at the very last place that it can represent a digit. So it rounded the 8 up because there would have been a 5 after it. So when we read a repeating decimal from a calculator, we have to be very careful of this round off error. Sometimes it will be tricky because it looks like the digits finish. In fact, it looks like the pattern breaks down because of the 9 at the end. But in fact, that is an artifact from the computer, essentially, that only allows the digits to extend to a certain place value. So we know better. We can tell that there's a pattern here repeating. 1 divided by 7 does appear to have the pattern 1, 4, 2, 8, 5, 7, and that is the repetend. There are 6 digits here, so our period is 6. Our next one, we have 2 over 13, so 2 divided by 13. Again, we have a lot of digits here, and it almost looks like maybe this is a terminating decimal, especially because our pattern almost breaks down. It doesn't quite continue all of the digits that we think it should. So 1, 5, 3, 8, 4, 6. Again, 1, 5, 3, 8, 4, 6, and then the last four digits, 1, 5, 3, 8. In this case, the digits aren't different than the pattern, but it's incomplete, like it got cut off. But again, that's just part of the artifact of the computer. It's only able to show you so many digits, and so at some point it has to round. So 2 over 13 would be the repeating decimal 1, 5, 3, 8, 4, 6. In this case, the period again is 6. We've got one more, and that's 5 over 18. So 5 divided by 18. This case, we do have a lot of 7s here, but the very last digit is not a 7, it's an 8. But if you had thought about rounding this number earlier, you could convince yourself that 8 is probably just representing that the 7s continue beyond the place value that the computer is able to show. So 5 over 18, we have 0.2. The 2 is not repeating, it's the 7s that are repeating, so I'll put the repeating bar only over the digit 7. In this case, the period or the number of digits in the repetend is 1. There's only one digit that repeats, it's the 7, over and over and over. Our calculator is kind of tricking us because it looks like it's saying, oh, it's a bunch of 7s until you get to an 8, but that's actually just a rounding error. We can use long division to justify how we know that for a fact the repeating decimal is supposed to repeat in those three fractions, that we're not accidentally reading the calculator wrong. So if we look at the fraction 1/7, that would say 7 dividing into the number 1. And I know I'm going to need some zeros here because 7 does not fit into 1. So we copy our decimal up, and then we start our division. 7 goes into 1, 0. 7 goes into 10 once, with 3 left over. 7 goes into 30 4 times, with 2 left over. 7 goes into 20 twice, with 6 left over. 7 goes into 60 8 times, with 4 left over. I need more zeros than I thought, so I bring it down. 7 goes into 40 5 times, with 5 left over. 7 goes into 50. Oops, not 6 times, but 7 times, because 7 times 7 is 49, with 1 left over. Notice that as soon as we get 1 again, we should start to suspect that we are right back where we started. And if you look back to a couple seconds ago in the video, this is the entire repetend. Once we get back to 10 down here, we know 7 goes into 10 once, with 3 left over, and the pattern is just going to continue. So it's really important that when you type a fraction into a calculator, you consider the possibility that there is an artifact that is causing a rounding error for the very last digit of your decimal. So if you see a pattern and that last digit appears to break that pattern, you should be suspicious that maybe that's part of the calculator artifact rather than part of the value of that actual fraction.